Okay, this is Physics Unit 4. We're on page 4, looking at number 9. This says class project, and normally how this works is each student would work on one of the lines, and we would come together and discuss. But we're going to do these all since we're not here, and this is just the video. A projectile is launched at 400 meters per second at various angles. So here's my velocity vector. I drew a little diagram. 400 meters per second and various angles. And the angle of launch that you see on the left side is against the horizontal. So 15 degrees is just 15 degrees above the horizontal, 30, and so on. For the horizontal velocity, Vx, we are looking for this component of this velocity vector. So I've drawn this diagram, I've made it into a right triangle, and so I can use SOHCAHTOA. So here's theta. I am looking for the adjacent side, and I know the hypotenuse. Adjacent and hypotenuse tells me that I need to use cosine. So horizontal velocity is 400 times the cosine of 15 degrees, which comes out to be 386.37, and that is meters per second. The vertical velocity component is the opposite side. So here's theta, we're looking for the opposite side. Vertical velocity equals 400 times the sine of 15 degrees. And it comes out to be 103.53 meters per second. Next is time of flight. So just based on the velocity vectors, we have to figure out how long this thing is going to be in flight. And only one of these two components will determine how long this is in the air, and that is the vertical component. The vertical component is affected by gravity. It will go up for some time, but gravity is accelerating it downwards, and eventually it's going to land. And so the velocity, vertical velocity, is going to determine the time of flight. And so we're looking at this one, 103.53. We're going to use formulas that are the same as in example 8 directly above in your paper. So we found one in 8C. It said what was the total time of flight. And so what we did was we found how long it takes the ball to get to its maximum height using this formula. Vertical velocity equals the acceleration of gravity times the time. And this tells us how long it went up or tells us how long it went down. And so we have to double all of this. And so what we're going to do is rearrange this formula to find the time. The time is vertical velocity divided by the acceleration of gravity times 2. We should even make the note here that this is up and down. And so if we put our numbers in here, we know the vertical velocity is 103.53. We know the acceleration of gravity is 10. And then we double that, and it's going to give us 20.705 seconds. We can use that one to find the range. To find the range, we are going to use horizontal distance equals horizontal velocity times the total flight time. We know Vx, we know T, we multiply them together, and we find that the range is going to be 8,000 meters. I'm going to leave a few rows blank, and you can take a look at them on your own. So I'm going to look at a 45-degree angle, and we find that Vx is 400 times the cosine of 45 degrees, and it comes out to be 282.84 meters per second. The vertical velocity, 400 times the sine of 45 degrees, 282.84 meters per second. The total time of flight for this one comes out to be 56.569 seconds, giving us a horizontal range of the horizontal velocity times the time, 16,000 meters. Skipping on down, I'll do the 75. The horizontal velocity component comes out to be 103.53 meters per second. The vertical velocity component, 386.37 meters per second. Remember, the time of flight is determined by the vertical velocity alone, not the horizontal velocity. And so the time of flight here is very long, 77.274 seconds. And then we find its range, that is the horizontal velocity multiplied by the time, and we find out that the range of this projectile fired at 75 degrees is 8,000 meters. So it looks like the maximum range for a projectile occurs if the angle is 45 degrees. And it looks like the range is the same for complementary angles. I'm going to go ahead and move on from part A and part B and look at the effects of air resistance. Now in this class, we always ignore air resistance. This is the only time in the whole class where we even really talk about air resistance because it's such a complicated topic. It works like friction, but you have to think about lots of factors like what's the temperature, what is the altitude, how dense is the atmosphere at that altitude, what's the surface area of your object, what's the shape of the object. It gets way too complicated, and so we ignore it. But here we have some actual numbers. These are for a projectile fired at 100 miles per hour at an angle of 60 degrees. So if this is the ground, we're talking about an angle something like this and 100 miles per hour. So the calculated numbers, the calculated time of flight is 7.89 seconds. The actual for the measurement is 6.55 seconds. It's the air resistance. And we can break this down even further the time up was 3.06 seconds. And then the time down is 3.49 seconds. So the air resistance is slowing it down on the way up, and then it continues to be slowed down by air resistance on the way down. Calculated maximum height is 250 feet. The actual, 173 feet. Again, this is the air resistance resisting its motion. The range calculated is 578 feet. The actual, 321 feet. And remember, our general rules was that launching speed equals the speed of impact. But when you include air resistance and you see that it takes longer to get down than it is to go up, it's not going as high as we thought, it's not going as far as we thought, the speed at impact is 65 miles per hour. And this all has to do with air resistance. The air is constantly pushing against this projectile and slowing it down. It is resisting its motion.